In the previous sections 11.3 and 4, we went through 3 important series testing mechanisms that are based upon positive term series. They are the integral test, the comparison test, and the limit comparison test, as summarized here. As you can see, we needed a continuous positive and decreasing function, eventually decreasing function for integral test. And for comparison test and the limit comparison test, both an and bn should be greater than or equal to 0. Now in 11.5 and 6, we're going to go through some more series testings, but they're not going to be bound to positive term series. The easiest of the bunch is the alternating series test, and it goes like this. We have to have an alternating sign, which is very, very conspicuous, as you can see here. -1 to the n minus first power. When n is running from 1 to infinity, you're going to get positive, minus, positive, negative, and so on. If you are negative, positive, and so on, then you can change it into -1 to the nth power. That is one of the 2 conditions for alternating series test, the easier of the 2, alternating sign. The second one is related to the absolute value part, Bn. That part must decrease down to 0. Do we have an example here? Let's go down, and here's one. This is clearly an alternating series. -1 to the k power, change the sign, alternates the sign. Now if I take the absolute value and remove this one, we have 1 over k log of k. Does it decrease down to 0 as k goes to infinity? Yes, it does. Consequently, this series converges by the alternating series test. In short, the alternating series test is very easy to apply, very easy to see. One more thing, this one is a little bit related to the proof of the alternating series test, but the proof of the series testing will be done in a separate video. So let's talk about this corollary just as a statement. We can estimate the error, that is the difference between the infinite series and then the finite series, and that can be estimated by an upper bound bn plus 1, the next term, the absolute value of the next term. I don't know how useful this will be. Now the next topic is the absolute convergence, and the proof is very, very simple as a matter of fact, but still I'm going to do the proof in the separate video. Proof is simple, but the statement itself is very significant. If a series converges absolutely, then the original series converges. What do you mean by absolute convergence? The series given by the absolute values converge. Then the original series also converges, but not vice versa necessarily. Here's an example. We have an alternating series, so it must converge. And if I remember correctly, this converges to natural log of 2. However, if you take the absolute values and remove this alternating sign, we have a harmonic series. 1 plus 1/2 plus 1/3 plus 1/4 and so on, that diverges to positive infinity. So here's an example of a series that converges but not absolutely. That kind of convergence is called conditional convergence. And this is an example of a conditionally convergent series, as a matter of fact, because if I remove this -1 to the k power and get 1 over k log of k, you can apply the integral test and prove that the resulting series given by absolute values is divergent. Here's the full solution actually. Converges because it's an alternating series. But if you take the absolute value, then you can apply the integral test, so it diverges. So we have a conditional convergence. Excuse me. We have a conditional convergence. How about the next series? This one is also alternating, and because we have -1 to the -1 to the nth power. But then again, how about this big one to the nth power? How does that behave? That's a little bit difficult to see. So to apply the alternating series test can be a little bit difficult. As a matter of fact, some other testing methods will be used for this one, by the way. That is, well, here. Ratio test and the root test. You can take the ratio of the next term and then the general term and then take the limit. If the limit is less than 1, then we have absolute convergence. Greater than 1, divergence. Equal to 1, inconclusive. You cannot quit the problem with inconclusive. That means I quit, I can't do it. Inconclusive means you must find another method. And this can be a little bit confusing, so let me help you a little bit. What do you mean by an plus 1 over an? Well, an plus 1 is the next term, isn't it? The ratio is less than 1 means the next term is much less than the previous term. We have quick decrease. How about this one? An plus 1 is the next term, and next term is greater than the previous term. You're not gonna have convergence there. Equal to 1. Okay, that's you don't really get confused there. In that case, ratio test fails. Root test is similar. We take the nth root of the general term, and then if that's less than 1, we have absolute convergence. Greater than 1, we have divergence. Equal to 1, well, inconclusive, which means you must find another method. Which test is more efficient in which case? Well, most of the time, really most of the time, ratio test is easier to use. Why? Division is easier computation than taking a radical. When did you learn division? In elementary school. When did you learn the nth root computation? In high school? Well, elementary school computation is supposed to be easier than high school computation. So, except for some special case where we have something to the nth power right away, ratio test is easier. I've seen a lot of students trying to use root test for the ratio test problem and really struggle. Sometimes they get it done, but in most of the situation they fail. Try not to use root test unless you have something like this, really conspicuous nth power. Well, let's apply root test here. If you use root test, then nth power is gone because you took the absolute value. This one is gone. All you have to do is calculate the limit of this fraction, and that's 2/3, certainly less than 1. Here it is. That's 2/3 less than 1, so we have to have an absolute convergence. So in this case, root test is working well. However, in something like this, it's gonna be ratio test. Well, factorial very strongly suggests ratio test will apply, because if you take ratio factorials, we have really simple computation. Here we go. If you take the ratio test, ooh, maybe I have to increase the font. It's very difficult to read. Okay, that's much better. Then this n plus 1 factorial and n factorial cancel out, and we just have n plus 1. And 5 to the n plus first power and 5 to the nth power cancel out, and we just have 5. How about n to the 5th power and n plus 1 to the 5th power? That's just algebraic. and that ratio, the limit of this ratio will just become 1 as a matter of fact. And in the end we have something like this, and that ratio is, excuse me, the limit of that ratio is 0, certainly less than 1. We have to have an absolute convergence there. How about some other example, like this one? That's going to be a challenge. Okay, I'm going to leave that to you. How about something like this one? Well, I think this should be a root test because we have nth power basically. Not nth power, n squared power, so it's going to be a little bit more complicated, but it's going to be a root test anyway. If you do that, nth test, because this is n squared test, and I take 1 over nth power for this nth root, we still have nth power left, and then after some manipulation you're gonna get 1 over 1 minus n to the nth power, and that's e to the negative first power. As a matter of fact, let's see, how do can I see this as e to the negative first power? It is okay, I'll leave that computation. Oh, wait a minute, I don't have to leave that computation here. The proof is right over here, right down here. This is a definition of E, so H is replaced by 1 over negative n, and then negative n over there, and then this negative n has to be flipped over to positive n, so we need this absolute value, extra negative first power. But of course, another way to handle this will be to use L'Hopital's rule. Take the logarithm and I put n outside and apply L'Hopital's rule, then you're gonna get whatever you were gonna get. And some other problems, let me see, how about this one? Looks like this is gonna be a ratio test, or ratio test, but I take it back actually. Ratio test is okay, but looks like you can do it better with limit comparison test, because growth order for denominator is 3 to the nth power. And how about this one? We could use ratio test directly, but I ended up using comparison test, or limit comparison test, whatever. In some cases there are multiple ways to handle the same problems, and you'll have to find a way to handle those. Well, we have all these series testings, and then we have some examples here, but there are going to be a lot more problems in WebAssign, so just practice those. We just went through 3 series testings here, alternating series, and then ratio test and the root test. Sometimes we have to consider absolute values, especially when we have alternating series, because the problem will probably ask you to determine absolute or conditional convergence. In that case, take the absolute values and then you'll have to apply another series testing, and that series testing can include the previous series testing methods, because by taking absolute values we ended up with positive term series. In short, we have to deal with all 6 series testing mechanisms, actually 7 if I count the nth term test for divergence. Well, when do we use which? Good question. We're going to talk about some shortcut method in the next video, but most of the time it is all case by case. You can get some kind of proficiency simply by doing a lot of problems and getting some kind of patterns. I cannot explain anything absolute because there are too many exceptions out there. Okay, we'll stop here. In the next video we're going to talk about rearrangement, and then some proofs.